everyone, welcome to the October Tech Forum. This is an opportunity for all of us kind of geeks in technology, and non-geeks as well, we're kind of an open community, to get together and learn about an interesting, exciting technical topic. And this month we're very, very lucky to have Simon Forman, the head of behavioural data engineering, which he said was a compromised title, and from the way I pronounce it, you can probably guess it's true. He's going to be talking about data engineering for the ITV hub. So please give it up for Simon Forman.
Thank you. Thanks, Tom. So, BDE, Behavioural Data Engineering. We are a team of engineers and analysts working with data collected as people use the ITV hub. I'm going to tell you a bit about what we do, the tools we use, and some of the challenges that we've had and solved. So, starting with what we do. We collect behavioural data. That's data sent back from the hub when people are using it. So it's the hub in all its forms. The website, apps, connected TVs, set-top boxes, you name it, we collect data from it. And we collect detailed video telemetry, every page visited, app journeys, device info, so about the hardware and the software running on devices, and a bunch more as well. So the detailed video is the bandwidth that the device is using, any errors that they're getting, things like buffering, if there's any interruption, and some of the experience metrics. So how long did it take to start playing? How snappy is the transition between ads? And the pauses between them. And as well as that, the exceptional things, we collect just normal, everyday heartbeats, just to say, hey, this person is still there, still watching, and we know that they're still viewing. So the data that we collect lets us and other teams answer these questions: who, what, where, when. About our audience and how they use the service. And there'd be no point collecting all this data if we didn't do something with it. We build and run systems that process that data, make it more valuable, more useful to us and other teams. We store it ourselves in lots of different forms, and we pass it on to other teams within the company. So one of our oldest processes is called the Stream Summarizer. And what that does is turn raw video data into a short summary saying who watched what, when. So the user, the content, when they started and finished playing, and an overview of their experience. Was it generally error-free? Was there some buffering? Or was it all good? And that's very useful for other teams' business insight, and anyone who wants a consolidated view of viewing. So they don't care about all the raw data. They just want to know, one record per stream. That's useful. For example, if you want to build a recommendation system, you don't need all the raw data. You just want to know, what's popular. This job turns hundreds of different events into just one single summary. And the processing actually happens while the video is playing. So events are streaming in, they get processed, and then the summary is ready as soon as the video is finished. And it comes out and it goes downstream into other systems, into other teams even. So another job is the sessionizer. It builds on the summaries that are emitted by the previous job, and it combines them with page and app data to give a view of the whole session that user had. So they might watch half a dozen videos, click around a few different pages, and this joins them all together and gives a whole view. It's very useful for tracking behavior, how people use the site. Do they search for something and then watch something else? Do they binge on something? Just watch, half a dozen episodes of one show back to back. And again, this is produced, and then we store it, but we also pass it on downstream to our consumers. So we run a number of validators. These are jobs that check the quality of the data that we're getting. They run all the time, they check all the data. They look for simple violations, so a numeric field that should that isn't numeric, or a simple typos, but also more complex problems. So we might have a situation where we say that an ad break's finished, but we never saw any mention of it starting. So that's sort of logical failure, and that lets us spot bugs sooner. So before we act on that bogus data and send it downstream, we can catch it. And another job we run is the one that powers this thing, which is the streaming status dashboard. What this does is gives many teams easy access to key hub streaming metrics. So things like volumes and the quality of service, all broken down by the type of device. So is it an iPhone or a TV, and by channel or VOD content. And this works by reading all the raw video events, doing some processing on them, and then emitting stats every minute. And that's in real time. So this graph updates all the time, and even during big events, we can see exactly what people are doing on the hub, how many people there are, and the experience they're getting. As soon as it's real time, right? As soon as it's happened. And being able to do that in real time is new for this system. We couldn't do this before we started using the tools that I'll talk about. At best, it was a few minutes old, and it couldn't handle big events. It would just be swamped and overloaded. And last service is the content ranking. So this is a service that tells you what content is popular based on who's watching it. It delivers a ranked list of popular content, and again, it's real time, so that when a popular show is available on the hub, then the list very quickly reflects that. So popular content is very quickly available for other people to find. So it sort of snowballs. Very good for something like TOWIE that is available right after broadcast. It's hugely popular online, and people appreciate that help finding it by it being on this list. It's used to power the front page of the hub. And we call this data platform, all of the collection, the processing, the delivery, we call it Crocus. So I'm going to talk a bit about the tools we use. We are big users of Google Cloud and all their products. Got nothing against Amazon, but Google was further ahead in some areas that we really needed. And we always try to use the highest abstraction level that we can. Things like serverless. There are data processing platforms that mean you don't need to worry about servers. Just write your app or write your procedure, and then it's run for you. And we prefer managed services where Google does all the operations and they just take care of all the sort of drudgery that you don't need to care about. We care about the high-level data processing parts. So a few of the Google bits, starting with Dataflow, which was the thing that drew me to the Google product in the first place. It's a serverless data processing product. You express what you want to do, how you want to manipulate data in code. We generally use Java, and it's run for you. And that takes care of all the kind of deployment things, the operations, scaling, handling failures. It's all done. You just write the kernel of the data handling. And crucially, it supports streaming jobs. where the input data never ends. So we've got jobs that have been running for months and months and months. They're never complete. They've never seen all the data they're going to. They just keep going 24/7. Data comes in and data goes out. And it abstracts away servers. So if one fails, you don't need to worry about what data is processed and whether it's contributed results to the overall total or anything like that. It's all done for you. And this thing has its roots in the original Google MapReduce system that had a really interesting paper. It was more than 15 years ago, I think. And a key benefit of data flow is it gives you correctness. Even in the face of delayed data or out of order data, you can be sure that the output, the results, will be completely correct. The next one is PubSub. Google call everything cloud something. So PubSub is queue as a service. It's hugely scalable. We've done more than 1.5 million message deliveries a second, and it's very easy to connect up other products using it as a queue and to provide a buffer between them. It's got a very simple programming model. You've got two things, topics and subscriptions. Subscriptions are associated with the topic. Every message sent to a topic is copied to every subscription, and then you can have independent consumers, each with their own subscription, or you can share a subscription between consumers. And equivalent in Amazon land is SQS. Cloud, again, functions. Almost the same as Lambda, if you've used that. Serverless application hosting. It scales all the way from 0 up to tens of thousands of invocations a second. The way it works, familiar model, you give it a small piece of code, that's your function. JavaScript is best supported, but there's more runtimes coming. And Google run it for you. It's that simple. Soon it'll support containers, so instead of a snippet of JavaScript, give it a container, and then they will scale that, run it for you up and down as much as you need. And take care of all the provisioning, capacity planning, all that stuff. And last one, BigQuery. So this is Google's data warehouse for huge data sets. And huge here means petabytes plus. It's got a really interesting architecture because it separates CPU and storage. So you can scale each one independently and just use as much as you need of each. So for example, if you run a complex query on lots of data, you'll just use loads and loads of CPUs, and temporarily, you'll just kind of borrow them, use them, run your job, and then they go back into the pool and somebody else uses them. But you don't need to worry about all of that. It's serverless, so you're not worrying. I mentioned petabyte scale, even because they're scaling independently. Even queries against petabyte-sized data sets are really quick, so under a minute. We use it just like a normal database for storing structured data, but also for raw data. We just chuck everything in. It's as cheap as normal storage, but with the benefit you can run SQL against it. We put all our every raw piece of data we have ever got, we're storing in there, log files, things like that. So, on to challenges we faced. First one, there's lots of data. Continuous, huge volume of data, like a fire hose. Close to 1 billion pieces of data on our biggest day, totaling hundreds of gigabytes. And it never stops. The hub's available 24/7, so our services need to be as well. Hub viewers never seem to sleep, so even at 3 a.m. we'll have tens of thousands of people watching Love Island when it's on. Students. So we can't have scheduled maintenance or unscheduled maintenance, especially for the collection parts, where we're collecting data in. If we're not available, that data is going to be dropped. Although saying that, our consumers don't really want downtime either. So they want a continuous flow of data as well. So one interesting problem we had is how to upgrade this summarizer job, the one I mentioned before. It runs all the time, and minor upgrades are easy. Data flow supports just an online upgrade. So that's if you make a small change to the code or want to upgrade a version of some library, that's easy. But sometimes there's a major breaking change, and that needs a stop and start. But this algorithm, the summarization, it needs context. It needs to see the whole data for a stream to be able to emit a summary for that stream. So how do you stop it and start it without losing that context? We can't tolerate any data loss. Our consumers depend on that. That's the contract we have. So what can we do? We need to do these changes, but we can't. So it's our version of changing the engines mid-flight. Right? The solution we came up with was to run a second version of the job in parallel. And the Google Cloud tools make it very easy to do that. PubSub, obviously, you just get a copy of the subscription. You get all the messages. You can run another job. You've got more CPU capacity available on demand. That's easy. And crucially, this job is started with a configuration that means it doesn't emit anything. It's just listening. It's doing all the work. It's computing summaries, but then it throws them away. Then when we've got both running happily, we configure a cutover time at some point in the future where we tell the new job to start emitting, the old job to stop emitting, and they use that time of day as a way to synchronize. And then when we're happy, the new one's going to take over successfully, we configure that, and then we just let them get on with it. The new one starts emitting, the old one just ceases. And we've done this a few times, it works really well. One point about the cutover time is it's in sort of data time. So any stream that has a timestamp after the cutover time is output by the new one and before by the old one. So we've done this a few times. It works very well, and it's a really nice model. There's no risk. At any point, you can back out, just kill the new one, and it's like you never started it.
How do you get the starting states from the old into the new?
You don't need to. So you say on Monday you start the new one, and it it fills up with state, and to start with it's emitting nonsense like half streams, but you're tossing those away so it doesn't matter. And after a few hours or a day, it's got all the context it needs to emit correct summaries.
It's like Windows, it's looking at a window of.
That's right, yeah. And by the cutover time, they should be emitting, if there's no code changes or algorithm changes, the same data. So a major challenge for us is data quality. You've heard garbage in, garbage out. That's very true for us. The contracts we have with our consumers promise high quality data, promise that we'll take care of any problems either by going upstream or by fixing them. So we can't just let crap go out. We've got a few tools that help us to keep on top of that. For the specs, where we say what we want people to send us, we make those machine readable. That removes ambiguity, and it enables automated testing. So developers, as they're building these things to send data to us, they can test before there's any, long before it gets to production. And I mentioned before we have validation jobs, so they flag up problems, and then we can go back and either fix the data if we can, or change the client system so it's not sending us bogus data. And the last one is we store all the raw data for debugging. So everything anyone sends us, we just keep it. It's so cheap, it's practically free, and it's often very valuable.
How big is that data set roughly?
Hundreds of terabytes, at least.
And over what period is that?
Just over a year.
Right.
So this summer we had a couple of massive events, the return of Love Island and the World Cup. So those were both predicted to be massive, based on previous form. And the challenge there is that our consumers want the same service, or even better. There's often more attention paid to the stats, so audience sizes, things like that, senior management want to know. Another challenge is that for Love Island, the viewers are very punctual. The show starts at 9 and they're there at 9, all 500,000 of them. That's hard for all of the hub services, but because we're collecting data, means a lot of the methods that you normally use to handle that load just aren't available. For example, you can't cache somebody sending us some data. And then England started doing well. They did much better than expected, and they smashed all the forecasts. So that was a challenge to handle that increased workload. We had just under 1 million people watching England's semi-final online, which was a new record by miles, and much higher than predicted. So we have a challenge to manage capacity. We have a very big difference between busy times, very busy times, and quiet times. We need to make sure we have enough capacity when we need it without spending too much, for example, by having lots available overnight when usage is generally really low. So we try and do that by making sure everything scales up and down, either in a magical serverless way, by using things like PubSub, BigQuery, Cloud Functions, or with more traditional instance group autoscaling when we have to. So magic autoscaling does work. The big promise of serverless, or one of them, is that you don't have to worry about operational things like capacity planning. And we've generally found that to be true. We have some fairly busy services running on Cloud Functions, and it's been generally rock solid, scaling up and down. And the managed things as a service products generally do work very well. BigQuery, database as a service, just scales, has handled everything we've chucked at it without any problems. We scale from 0 to our busiest times without any intervention. PubSub is a really good example. Setup is just picking a topic name, and then you're off. There's no difference between one that handles a message a week and 1 million a second. Same for functions, 0 to tens of thousands per second without any changes. And our choice is always to use this model when possible. Let the cloud do the hard work. So there's not much more to say about that, it just works. But when we can't use that, we have to use traditional autoscaling. So that's instance group autoscaling, where you have a group of identical servers, and they're automatically added and removed due to a changing workload. This needs more engineering effort. You have to choose the right metric as the trigger. You need to tune the thresholds both up and down. Usually that trigger is that metric is CPU, but it could be anything you like: a queue's backlog, service latency, whatever's appropriate for your app. And you need to build your app to cope with instances suddenly appearing, suddenly disappearing. For example, if you need to reshard your workload across servers, or a server that comes up has a cold cache, so it's useless until it warms up. You need to handle that. And on the way back down, if you are killing an instance, you might want to transfer data off it or do some cleanup stuff. You need to be ready to handle that. And lastly, there might be an impact on dependent services. If you suddenly have twice as many servers hitting a database, is it going to fall over or is it okay? But auto-scaling is slow. Depending on the app, it can take, best case, 2 minutes. We've seen up to 15 minutes for a new instance to actually start being useful. And that's longer than most services can afford to wait. If there's not enough capacity, the red part of the graph, you risk an outage, unhappy users, and that outage can last long after the extra capacities come online. You're struggling to recover. So you've got this capacity gap that you need to fill. If you could just get through this period, while more instances are coming online, that would be fine. Autoscaling would manage to handle the normal ups and downs of your service, but you've got to get through that gap. So the answer we found was to reserve lots and lots of headroom on every instance. So, for example, run at 20% being the normal usage. And that's bogglingly low. Normally you'd run at 80, 90% to get the most value from that instance. So if you're at 20% normally, you might scale up at 25 and down at 15. But to try and keep 20 as your sort of normal. And that means you've got reserved capacity on that instance. It's already provisioned, your app's running on it, and it's available immediately as soon as it's needed. So a way to fill the gap is to use the instance headroom. You trigger auto-scaling normally when the workload starts to increase, but you handle that increase in the short term with the already existing instance capacity. And then later, when auto-scaling does manage to add some more servers, it bumps the capacity up, ready for the next increase. And this two-speed scaling means that you can handle very sudden increases in workload. This graph is from the England semi-final, just going into an ad break. And simulcast actually works really well to coordinate DDoS attacks. Everyone hits the service at exactly the same time. So from the left, the workload increases very sharply. That's the blue line. It goes from about 40,000 requests a second to 100,000 a second in about 14 seconds. The capacity, that's the yellow line, so this is an auto-scaling thing, does increase, but not for a couple of minutes afterwards. It's still pretty snappy. It's good, but it's too late. You don't have 2 minutes. You've got 2 seconds. And this worked perfectly. We handled all those requests. Yeah, no problems. This is the Love Island final. Similar graph. This is the 10 minutes before TX starts, so 10 to 9, 9 o'clock. And that workload more than doubles in about 5 minutes. You can see it getting really steep towards 9 o'clock. Auto-scaling on its own just won't handle this, you'll be flattened. But again, we handled this perfectly. But if you're paying for 100%, but you're only using 20%, that seems like an expensive way to run a service. And it is. But that might be acceptable compared to other ways of handling a variable workload. You might try and do fixed capacity, where you have the same number of servers 24/7, and you just work out what your peak's going to be and scale for that. But that leads to lots of wastage, except during the very highest peaks. You're basically always under your peak. Or you try and look at the schedule and say, how big is this show going to be tonight? And then forecast your demand and get the right number of servers available ahead of time. But that's very hard to get right. And if there's any surprise in the schedule, you've got no chance. And it's risky. If you don't get it right, you aim too low, then again you're into that out of capacity situation. But when it's working, allocated capacity, that is how much you're spending, does quite accurately track the workload. It does this staircase pattern, but it's generally a little bit above it. And you can choose parameters depending on the nature of your workload, how quickly it changes, and also how much it changes. So during that auto-scaling lag period, that informs the parameters you choose. If it can double in that period, you might run at 50%. If it can go up tenfold, which is what we see, 10% would be a better choice. So Amazon has a great product, T3 class instances. They call them burstable instances. These are like normal EC2 servers, but with some unique features. They're a fraction of the cost. That's the best feature. For example, they're a tenth of the cost of a similar normal server. And that's without any reserved capacity or using the spot market or anything like that. They're just normal servers. You pay for them by the hour, no commitment, and they won't be terminated from under you. The downside is they have a tenth of the power, right? A tenth of the cost, tenth of the power, so it's fair. And that's an average over a day. So you can still use full power for short periods. As long as you keep the average low, then you're good. And that makes them a perfect fit for this kind of auto-scaling. Low normal utilization, but with occasional spikes up to fill those auto-scaling gaps. And you've got capacity available for the short spikes without having it available all the time. So using these burstable instances, you get the benefits of instant auto-scaling without any extra cost. We used this system actually on AWS before Google for a couple of years. The threshold was set to 10%, so our instances were always at around 10%, which seems mad, but it works really, really well. When we have something like an ad break that generates a surge of data, they might go up to, 80% briefly, and then auto-scaling makes some more and the average comes right down. Like I said, that ran for a couple of years, very successfully, and it was really cheap as well. So to sum up managing capacity, if you can, use serverless or a managed platform, but if you can't, then you could do engineering work to make traditional auto-scaling work really well for variable workloads. We've managed to make it responsive, so it can handle quick changes in demand, and shown how to make it either compare favorably or actually be no extra cost if you use Amazon's burstable instances. And we ran this throughout the summer, so that's World Cup, Love Island. It worked really well. We didn't have to lift a finger. We weren't trying to do anything when England started looking like they might win the final. We didn't need to provision more capacity or do anything. We just let it scale up. So that's me. Thank you. We're hiring. So if you like the sound of doing that kind of work, drop me a line, or I'll take some questions.
Are you multi-region? You don't need to do that?
We are not multi-region at the moment, no. I'd quite like to, just for reliability, availability, but it's not pressing because the region we're in has been so reliable. We're multi-availability zone within one region.
What about functions, cloud functions? So Lambda on AWS, typically people think, oh, amazing, just eval in the cloud, it'll be instantaneous, but there's a lot of latency and it's warm-up kind of costs, and it's better with JavaScript than it is with Scala or Java or whatever. How is that?
I think there's still a cold start penalty. So if your service gets, say, 1 hit an hour, that 1 hit will be really slow. We tend to get continuous volume, so we don't get big gaps between hits that let things cool down. Or we do have services that aren't very rarely hit, but it doesn't matter if they take a couple of seconds to start up. Yes, you're in the front.
Is Splunk still part of your stack at all?
Splunk is. It's used as an analysis platform, but it's not a primary collector of data. So we feed it heaps of data and use it for complex queries, but it's not the only place that data goes into.
What are the other kind of consumers on the other end of the pipeline?
We put lots of stuff into BigQuery, and people are, rather than us moving the data, we're moving the people to BigQuery so they can do their work there. We send a lot of data to SVV, so that's single view of view. It's a big database of all of our customers' interactions with the hub and information about them, the person, as well.
Do you have any big challenges about schema changes and representational changes, discontinuities, how you represent and stuff?
It's fairly stable. We've had to do some changes. The challenge there isn't so much that changing the schema means it's any kind of outage or anything like that. And generally, we're just adding columns, so there's not much challenge there.
Are the specs for the events you consume available anywhere?
They're on GitHub.
Okay, cool. That includes all the metadata you send alongside the.
Yeah, the whole thing, the whole spec for what we collect or what we ask the teams that build the hub to send us is all there on GitHub.
Okay, but is that like a JSON schema?
Yes, yeah, it is actually.
Okay, cool.
Mark.
You go.
So I was wondering about some use cases of the consumers of your data. Do you use this data for providing personalized experience for the customers?
Yes,
on
yes.
a real-time basis as well?
A couple of examples. We drive the most popular feed, which is not personalized to a user, but it's personalized based on everyone's usage, and that's real time. That goes straight back into the hub as as the front page. Sorry, what was the other part of your question?
So I was more interested in personalized
Okay, so
user
we
experience.
feed SVV with a feed of all of the stream summaries and page views, and that's used to give personalized recommendations about content people can watch, and it drives marketing activities. So push notifications for, hey, you might like to watch this program, that kind of thing.
And is that used for advertisements as well?
Our data isn't used for advertising, I think. Not directly. Mark?
How was your? So you said that it kind of sounds like it kind of takes care of itself. So the Love Island World Cup 2 months beforehand, fear of everyone testing all their services. What was your preparation there?
We did that. We load tested our services to the big numbers that we forecast, and I think with barring a couple of minor changes, everything just scaled up and scaled back down again.
You still did all that for all that time to test it anyway?
Yes.
So you're not at that point where you just go,
No.
always on.
No, I think we have a lot more confidence after last summer. But for any new thing, you can still have surprises. Something doesn't perform as you expect at scale. Trust but verify. Tom?
What's next?
What's next? There's a project underway to capture data from linear viewing. So not just the hub online, but normal television, which will be obviously a lot more data, and that'll have different applications, different consumers. Yeah.
That way you're hiring.
That's, yeah. Hi.
Did you have to do any extra work because of GDPR? Would you like to keep the mass release in the cloud since they are significant use, for example?
We didn't have to do anything differently. We were already doing things like encrypting in flight and at rest, and the other parts about deletion of personal data. We kind of tie into the hub's other data storage systems.
Thank you.
All right, thank you.
So if you fancy being up here where Simon is standing this time next month, kind of please give me a shout. Always interested in kind of new tech talks, or if you know people from outside of ITV as well, who you think might be kind of interested to kind of speak as well. We do welcome kind of external or special guests. And I think that's it for today. The only other thing is to mention the Tech Social is happening at the Eastern, as always, at 5:30 this afternoon. So if you fancy that, wander over and have a beer or a soft drink as well with one of your colleagues. So thank you all for coming, and see you next month. Cheers.